Good morning. I hope everyone enjoyed or survived special relativity, maybe both, survived and enjoyed. We're moving on now. We developed some important concepts in special relativity that we can now apply. We're getting ready to move on to quantum mechanics. So we've got a couple chapters, chapter 37 and 38. Kind of by tradition, I guess, physics textbooks kind of like to tell the story of the development of quantum physics. So chapter 37 is referred to as early quantum theory. And also important in this chapter is we're going to start talking about atoms and the physics of atoms, how we understand atoms. So we're going to talk about models for that. So let's go ahead and get started here. Again, I'm going to go through these. I'm going to go through the list here pretty quickly, and we're going to jump in and start talking about thermal radiation, or what's called black body radiation. So all objects emit light in different parts of the spectrum, depending on what their temperatures are. Objects like stars that are at really high temperature, a lot of the light they emit is in the visible part of the spectrum, and so they light up. We can see those objects. But objects like planets, like Earth is radiating too, but the light coming off the Earth is in the infrared. So in the infrared part of the spectrum, that doesn't show up so that our eyes can see it, but if you had night vision goggles, then you would see everything lit up surrounding us with infrared. So anyway, all objects emit light. That's what the radiation is referring to here. It could be at different parts of the spectrum. It could be in the infrared, it could be in the visible, it could be in the ultraviolet or the X-rays or the gamma rays. And the intensity of that light is proportional to the fourth power of the temperature of the object that's radiating it. Now you guys may remember this from Physics 4b back in thermodynamics. We talked about radiation as a method of heat transfer. And there was a temperature to the fourth power. We're going to come back and revisit that and get a better understanding kind of at the quantum physics level of what's going on. So this light or thermal is called thermal radiation. It has to do with what the temperature of the object is. Now, in particular, black body radiation is thermal radiation where the object is perfectly absorbing. So think of this as a black object where the light comes in and every photon of light that comes in gets absorbed. And so it absorbs and emits light. I'm going to say perfectly in quotations here. And we'll see what perfectly means. But for light coming in, it means everything gets absorbed. And then for that objects that are good at absorbing light are also good at emitting it. It turns out that there's a direct correlation between absorbing light and radiating light. So those go hand in hand, those two effects. And so a black body is one that is perfectly absorbing and emitting, both absorbs and creates light across the entire spectrum. So now there have been measurements. These experiments go back into the 1800s. And so what people were observing back in the 1800s, the later 1800s, is they were doing these experiments, they were heating objects up, and then they were measuring the light. One of the favorite ways to do this was to build a hollow container, maybe it's made out of steel or something, and bring it up to a really high temperature, and then put a little hole in the container to sample the light that was inside. We're used to thinking, oh, here's a container, here's gas molecules inside. Well, it turns out that in every container, there's also photons that are being generated inside. So they could sample the light coming out of the container and look at the range of wavelengths. So they would look at the wavelengths on the chart we have here, we've got wavelengths listed in nanometers, 0, 1,000, 2,000, 3,000. The visible part of the spectrum is between 400 and 700 nanometers, so it's that narrow region right there. Things to the left are at shorter wavelength, that's UV, and then things to the right at higher wavelength, those are infrared. And so what they found was, when they heated something up to, say, 3,000 Kelvin, it would begin to glow with visible light. If something was down at room temperature, the only thing being radiated was pretty much in the infrared. But once you got up to these higher temperatures, you would start to produce visible light, and as you went to higher and higher temperatures, it was determined that the intensity of the light per wavelength shifted so that more and more of the light energy was being generated at shorter and shorter wavelength. So it's like heating something up, and at first you're getting a little bit of the red part of the spectrum, and then you heat it up some more, and you start to get orange and yellow, and you go up to these extraordinary temperatures, thousands and thousands and thousands of Kelvin, and you can get things to glow blue. Okay, so that's what they're observing. Now, wavelength is listed at the bottom, frequency of the light is at the top. So I just wanted to add this chart in, and the reason for my wanting to add this chart in is the textbook is a little confusing, I feel like, about what this graph really, what the axes refer to. So the way this works is, here's our thermal radiation graph, and it corresponds to a particular temperature. This function that they plot in the textbook over and over, and we're going to see a number of slides of this. The way that we determine the total intensity across the entire spectrum. So an object is radiating light at a whole range of different wavelengths. And here is the wavelengths, and then the height of this function tells us how much intensity we're getting at each particular wavelength. So it's a function of wavelength, and that's what I've called it. Now, if I integrate across that function, what that tells me is I'm getting the total amount of energy. If instead of wanting to get the total intensity, the total energy per area per time, instead of getting the total energy, if I just want the energy associated with one particular wavelength, then what I have to do is look at a narrow region over here that has a width of d lambda. So this should sound like calculus, right? So there's going to be a narrow column there. I can identify d lambda as maybe 1 nanometer. You know, I could be looking at a wavelength of 400 nanometers. So if I look at the range of wavelengths within 1 nanometer of 400 nanometers, maybe between 400 and 401, I can calculate the intensity there by looking at this function. That's actually what this function tells us. And what that is it's d lambda. It's the intensity, watts per square meter, for, say, each nanometer vertical strip. So the area of that narrow strip is the portion of the intensity being contributed by that particular wavelength. When I add them all together, I get the total intensity, or I can break this down into how much intensity at each particular wavelength. Now, a couple of features that they talked about in that previous slides. These were noted, again, back in the late 1880s, 1890s. People are carrying out these experiments, and what they're noticing is that the peak wavelength, the wavelength at which the intensity is the very highest, could be determined by this formula. It was inversely proportional to the temperature. So they could raise the object up to a higher and higher temperature, and they could watch the peak wavelength shift. And they found out that there was this very directly inversely proportional relationship with this constant. This is called Wien's law, and the constant here is 2.90 millimeters kelvins. So if you tell me the temperature of the object, this formula tells us what wavelength will be producing the highest intensity. Okay, and they had diffraction ratings. So you could take the light coming out of one of these devices that they had built, and you could analyze the light. You could separate it out, and you could see how much of each different wavelength, how the intensity compared across a first order spectrum of light coming out of a diffraction grating to carry out these experiments. This is kind of extraordinary. You always think going back 100, 120, 140 years, the tools that people were working with and the discoveries that they were able to make. The other thing that they talked about on those earlier slides is, what was also found was that as they went to higher and higher temperature of the object, the intensity of the light that was being generated when those objects would glow red and then yellow and then green and then blue, it varied like the temperature to the fourth power. Now, we don't have that many formulas in physics that are to the fourth power. This is a really dramatic increase in the way that the energy goes up as we go to higher. So doubling the temperature of an object increases its intensity by a factor of 16. All right, and of course the temperature's on the absolute scale, so that would mean if I went from 1,000 Kelvin and then I went to 2,000 Kelvin for the temperature of an object, you would be having 16 times as much energy being produced at 2,000 Kelvin compared with 1,000. So that radiation effect goes way up really fast. Let's try these two formulas right there. Let's try them out. Oh, this is called the Stefan Boltzmann constant, 5.67 times 10 to the minus 8 watts per square meter per Kelvin to the fourth. The units in these constants are there to make sure the units match up. And this is our 5, 6, 7, 8 constant. So that one's easy to remember, right? 5, 6, 7, 8. Let's estimate, or let's look at the surface of the sun and estimate what its temperature is. Now, we haven't taken a thermometer up to the sun and stuck a thermometer into the sun and looked to see what the temperature is. Instead, what we've done is we've looked at the pattern of thermal radiation. So when we look at the thermal radiation coming off of the sun, it peaks around 500 nanometers. So again, we take sunlight, we take it through a diffraction grating, and we look and we go, oh, the intensity is the highest here at 500 nanometers. Now that gives the sun its color, kind of that yellow-white color, comes from the spectrum of light being produced. But we can take Wien's law right here, and we can plug numbers in. So I'm going to plug in the wavelength, 500 nanometers. Now that constant A can be written as 2.9 millimeter Kelvin, but we want to use nanometers. So when we're using this for nanometers, for visible light, we got to put in 2.9 million. Now I should have used scientific notation. I apologize for all the zeros. I kind of like writing lots of zeros for some reason. I need to stop that. But the temperature we came up with is 5,800 Kelvin. So that's pretty cool. Now that's the surface of the sun. The light spectrum that we're looking at was generated in the outer layers of the sun, not at the core. The energy is generated at the core, but as it makes its way, as the energy gets transferred to those outer layers, the light we're seeing, the photons we're looking at, were actually generated by the gases, by the material in the outer layer of the sun. So the outer layer of the sun's at 5,800 kelvins. We can also calculate the intensity of light. I can plug in that 5,800 Kelvin to the fourth power, put in the Stefan Boltzmann constant, keep track of all my units, and I ended up with 64 million watts per square meter. So if we take a field trip, maybe we can get Laney College to pay for this, take a field trip to the sun, and then we take our 1 square meter with us, because every physics student has a 1 square meter that they carry with them. Take our 1 square meter and put it along the surface of the sun. Every second, we're going to have 64 million joules of radiant energy coming off the surface. That's a lot of energy, and it's a really high intensity, which you would expect for an object at 5,800 Kelvin. If we reproduce that object in a laboratory on Earth, 5,800 Kelvin, that's what we see. We see that 64 million joules every second per square meter of energy coming off. Now, from that, we can take the surface area of the sun and multiply by the intensity to get the total energy output of the entire sun. So the sun's total energy output, 3.9, 10 to the 26 watts. It's a really big light bulb. Now, compare this with Earth. So with Earth, let's start off and say, okay, the surface of the temperature of the Earth is like 300 Kelvin. What would be the peak wavelength? Now, like the sun's producing a whole spectrum of light. Earth is producing an entire spectrum of light. And if Earth is at 300 kelvins, then the light coming off would peak at a wavelength of 9670 nanometers. Now that's quite a ways off into the infrared. That's not anywhere near visible light. We would need to have the temperature go up, 10 times as much to be able to start seeing significant amounts of visible light generated by Earth. Okay, we're just not at that temperature. But plenty of infrared coming off. Let's see what the intensity of light coming off the surface of the Earth is. If we use the temperature to the fourth, 300 Kelvin, and this Stefan Boltzmann constant, it says, all right, 459 watts every square meter. So, well, that's a lot, right? If I take, the square meter that every physics student and physics teacher carries with them, put it on the surface of the Earth, set it there and go, okay, that's the rate at which energy is being radiated back into space from the surface of the Earth. It's being radiated at 459 watts per square meter. If we integrate that over the entire surface of the Earth, that's 2.34 10 to the 17th watts. So that's the rate at which energy is being radiated back out into space from the Earth. Okay, that's a good rate. Now, if we slow that process down, the temperature of the Earth will go up, and that's the issue with global warming. So the idea is we put more and more carbon dioxide, more and more methane, and even more water vapor into the atmosphere. Carbon dioxide, methane are going to be absorbing the infrared coming off the surface, and it slows the process down. It's like putting a layer of thermal insulation around the Earth where the sunlight is able to come in through the insulation doesn't block, the carbon dioxide doesn't block visible light, but it blocks the infrared coming back off of the surface. Okay, so that's how it works, and I'm sure you guys have, you've discussed global warming issues in other science classes, but now we're at a point where we can start to actually talk about what are these rates? What's the rate of energy coming in, being received through sunlight with the Earth, compared with the rate at which the Earth itself is radiating, and what carbon dioxide and methane are doing is slowing down that process. All right. While the sunlight's still coming, it resets the equilibrium temperature for the Earth. Well, let's take a look at that example. So let's say, using kind of the same arguments here is a star somewhere in our galaxy, and here's a planet orbiting the star, and here is light from that star coming in. This could be sun and Earth, right? Now, at the surface of the star, there's a certain intensity, and we just calculated that. But the intensity of sunlight or starlight at the surface, it's not the same thing as the intensity of sunlight at the planet. The light heads off in all different directions, and that means that by the time the sunlight or the starlight reaches the planet, the intensity will be much reduced. Now we can calculate that. What we can do is we can say, okay, here is the intensity at the surface. Here is the total energy output of that star. It's the intensity at the surface multiplied by the surface area. And the surface area for the star is 4 pi r squared, where r sub s is the radius of the star. And the sigma, Stefan Boltzmann, times the temperature, the surface temperature of the star to the 4th power. Now, by the time it reaches the planet, and I'm calling this intensity of starlight reaching the planet. I don't know if that was the best. I'm going to stick with it. So this is the intensity of the sunlight once it's traveled the distance little r. So notice little r is the distance center to center from the center of the star out to the center of the planet. And the diameter of the planet and the diameter of the star don't affect this much. But all the formulas we're working in terms of here are center to center calculations. So I need to know the distance out to the planet. I need to know the radius of the planet's orbit. And this is telling me now that, the 4 pi's cancel out. The intensity of starlight, once it reaches the planet, is going to be sigma. It's the original intensity, but multiplied by this factor. So it's the r squared effect. As the sunlight spreads out, the intensity drops off. Okay, that's at the location of the planet. This is how intense the sunlight's coming in. Now let's look at the planet. Now if I think of the planet here, it's got sunlight coming in, but the sunlight's not coming in from all directions. The sunlight, or starlight, is only coming in from one direction. So that means if I look at the rate, the power of sunlight coming in, that's the intensity of the sunlight times the cross-sectional area of the planet. The planet, if I'm looking at sunlight traveling pretty much parallel towards the location of that planet, the planet creates a pi r squared a circular cross-section. So I only want to include a circular cross-section of planet that will be absorbing the sunlight. Now, the planet's not perfectly absorbing, but it turns out that's not, well, in more detailed calculations, we would have to keep track of how the absorption varies across the spectrum of light. For our purposes, we're just going to treat this as there's a certain factor that gets absorbed and there's a certain factor that gets re-radiated, and to first level approximation, those are the same factors. So we're going to ignore that effect. So we'll say the power coming in, let's treat it as if it's all absorbed, and then the power of light leaving, which we just calculated. We calculated what's the rate at which Earth is radiating back out into space, and I'm going to set those equal. Now the argument here is, once a planet has been around for a while, and the sun has been radiating for a while, the sun's sunlight rate coming in isn't going to change very much. And that means that the planet adjusts its temperature until we reach equilibrium. If the sunlight coming in is more, then the temperature is going to go up. As the temperature goes up, the planet begins to radiate more, and so there will always be an equilibrium temperature that we reach when we've got these two radiative energy transfers taking place. So what I'm going to do then is, now there's a factor of 4 on the direction outwards because the planet is radiating outwards in all directions. So the light's only coming in from the direction of the star, but it's being radiated out in all directions, and that introduces a factor of 4 because of the surface area of the planet. So when I substitute in the expressions that we derived for the intensity of the sunlight and for the intensity of the planet, the Stefan Boltzmann constants cancel out, and what I'm left with in the formula, it actually turns out that the radius of the planet cancels out of the calculation. It canceled out right here when we were looking at cross-sectional areas and surface areas. So the temperature of the planet, it doesn't depend on how big the planet is. Now it does depend on how big the star is. So the radius of the star is still present, It depends on how far away the star is, and it depends on the surface temperature of the star. So depends on the surface temperature of the star, how big is the star, bigger stars, more energy being produced, and then it depends on how far away the star is. And that's it. The simplest model looks something like this. Now we can put in the temperature of the sun, 5,800 kelvins. The radius of the sun is about 700,000 kilometers. And then what else? We need the distance to the Earth. So center to center distance here, 150 million kilometers. And I plugged into our formula. This is the formula from the previous page. Now I simplified it. I took a fourth root. And this simple model predicts at equilibrium a planet located where Earth is, away from the sun with this temperature and size, should hit equilibrium at 280 Kelvin. And you go, that's a pretty good prediction. That's not bad at all. That's about the surface temperature of Earth. Certainly in the polar regions, that's probably too high. Near the equator, that's probably too low, but as far as an average daytime, nighttime, polar, equatorial average, 279 kelvins, that sounds like Earth. So it turns out Earth's atmosphere is thin enough that it doesn't have such a big effect, and this simple model works pretty well. Let's move on to Mars. Now, there have been those absolutely amazing videos, I hope you guys have seen this, of the Perseverance Mars rover, the Mars lander, being lowered onto the surface by the descent spacecraft. When was this? Just a few days ago. Absolutely amazing. And the videos are so good now that it's just absolutely amazing to see this. I see something like this and I think, oh my gosh, physics, engineering, the sciences, that's the place to be. This is totally cool. Total exploration of our solar system. So looking at Mars, Mars is farther away, and that's the only thing I have to change, right? In the formula, the only thing I need now is to take into account the additional distance. And for Mars, it predicts 228 kelvins, and if you've been following temperature data on the surface of Mars, you go, oh my gosh, that's right on target too. That's basically the temperature on Mars, is, minus 40 Celsius, minus 40, 50 Celsius. That is the surface temperature. So that's two successes. That's 2 for 2, right? We got Earth's temperature using this simple model, Mars temperature using this simple model. Again, Mars has an even thinner atmosphere, and so even a smaller effect on the sunlight coming in versus the rate at which energy is radiating off of Mars. So at 228 Kelvin, we can calculate what's the total rate at which energy is being radiated away from Mars, what's the total sunlight coming in, and at this temperature, those two balance out. All right, let's move on to Venus. You guys probably know Venus is not a success story here as far as using our simple model. If we put in the values for Venus, now Venus is closer, it's at 108 million kilometers from the sun, center to center. The prediction is 329 kelvins, almost tolerable if you built really good air conditioning systems on Venus. But the observed surface temperature, 740 Kelvin, not even close, right? We've got a temperature here more than double, and this is on an absolute temperature scale, more than double the predicted temperature from our simple model. What went wrong? Venus has got a really thick atmosphere, and the atmosphere is almost entirely carbon dioxide. So this is what happens if you take a planet. Now compared with Earth, Venus has like 100 times as much carbon dioxide, or let me take that back. It's got an atmosphere that's 100 times denser than Earth's. Now Earth's atmosphere is predominantly nitrogen and oxygen. Only 400 parts per million of Earth's atmosphere is carbon dioxide. Most of Earth's carbon dioxide from formation of the planet is now part of the rocks. It's part of sea creature shells. So anything that's a carbonate used to be CO2. I used to, 20 years ago when we had chalkboards in our classrooms, at this point I would pick up a piece of chalk, which I could have brought with me. I would pick up a piece of chalk and say, here it is. Here's where Earth's carbon dioxide ended up. Calcium carbonate. So on Venus, that didn't happen. Venus's carbon dioxide stayed in the atmosphere because Venus was at a higher temperature already, 329 kelvins is what we're predicting. And at that temperature, water didn't remain liquid on the surface. So we had a lot of water vapor that would go into the atmosphere, and then at those, the water vapor in the atmosphere would get dissociated and then head out to space. And so little by little, Venus lost its oceans, and CO2, carbon dioxide, was not able to dissolve into the ocean. So it's released back into the atmosphere, nowhere to go. As a result, temperatures began to go up. And so you've got this runaway greenhouse effect, where as the temperatures go up, more and more water vapor, more and more of the oceans vaporize. They're lost to outer space. These water molecules get dissociated by the UV light, and all of the carbon dioxide back into the atmosphere. And so that's an example of, runaway greenhouse effect. Venus's atmosphere is 100 times denser than Earth's, and it's almost entirely carbon dioxide. So hundreds of thousands of times the amount of carbon dioxide. And the temperatures have just taken off. Okay, no more liquid water on the surface. All of the CO2 returned into the atmosphere. All right, so good planetary comparison here. Two where the simple model works really well. One where it doesn't. We don't want to follow that example. We want to stick with the lower CO2 concentrations in our atmosphere. All right, one more example that they've got here with the color of a star. What would happen if a star's surface temperature, 32,500 kelvins? What color would this star appear to be? And we can use that Wien's law. So here's Wien's law, here's our star. That's much higher temperature than the sun. Sun was at 5,800 Kelvin. This is like, 4 or 5 times? 5 times the temperature. It's going to be radiating 5 times 5 times 5 times 5, 625 or something. It's going to be radiating a lot more intensity. The peak wavelength for this star is 89 nanometers. Well, that's in the ultraviolet. So if you have ultraviolet eyes, or if you have ultraviolet devices that can see in ultraviolet, then the star lights up, its peak wavelength is ultraviolet. Now, if your eyes are limited to the visible part of the spectrum, then it would appear blue or violet, a blue-violet star, because if we, again, look at that peak, if we look at that distribution, what we're going to start calling the Planck distribution of light, now it peaks in the ultraviolet, and so the visible light is out on this tail. Most of the light that's being produced is ultraviolet. All right, let's go back and talk a little bit more about this Planck distribution. So here is the Planck distribution, that red line, and here is, now they've switched this over to frequency, which I wish they wouldn't do. I wish they had stayed with wavelength. But what this is showing is going higher in frequency. Let's think of it this way. When you're going higher in frequency for the light being produced, that's shorter and shorter wavelength. So let's think of this as really long wavelength, shorter and shorter wavelength. Now, at the time when these models were being developed, the idea was as you went to shorter and shorter wavelength of light, there are more and more ways to have shorter wavelength than there are longer wavelengths. I mean, that statement sounds a little funny, but the idea is, imagine taking a box. How many different ways can you fit long wavelengths into the box? And it turns out there's only a few ways of fitting long wavelengths that meet the boundary conditions of the box. Now, as you go to shorter and shorter wavelengths, there are more and more ways to fit those shorter wavelength patterns. It's kind of the wave pattern that fits inside a box. And so the prediction here was that as you go to shorter and shorter wavelengths, we should be seeing more and more energy, more and more intensity should be at the short wavelengths rather than the long. It wasn't happening. So, and the reason I put this slide in here is to be able to tell you guys, this was called the ultraviolet catastrophe, which I figure should be the name of a rock band or something, right? The ultraviolet catastrophe. And the idea was, in going to these shorter wavelengths, theory was predicting there should be higher and higher intensity, but there wasn't. And so it was a catastrophe, I guess, for the physics community, for the theorists that were trying to explain what was going on. Well, Planck came along. Planck was a good physicist. He was a really sharp mathematician. And Planck tried to come up with a formula, tried to come up with some type of a principle that would predict what was being observed. So this red line is what was being observed, and Planck played around with different formulas until he found one that matched the experiment. Now, that's not unusual in physics. A lot of times theories don't just come out of nowhere. People are looking at the experiments and saying, what type of a formula is that curve, that experimental curve that we're seeing? And so Planck found that if for every frequency of light, every wavelength of light, every frequency of light, if he assumed that there was a certain amount of energy, that the curve, mathematically, that he ended up with looked like the experiment. Now, let's think about what this means. It says that if you had short wavelength light, say the blue end of the spectrum, for example, that would be high frequency, that would be higher energy. So the argument here from Planck was, it's harder and harder to produce ultraviolet light because it requires more energy. Now, Planck took this mathematical formula that he came up with, and he developed the Planck distribution. Let me go back and look at it. So by assuming that each wavelength required a certain amount of energy, he was able to produce a theoretical plot that matched the experiment. Now, Einstein came along and said, you know, what you're talking about are particles of light. And the idea that light consisted of particles, it wasn't new. This went all the way back to Newton. Newton had suggested that light was made out of particles. But for a couple hundred years, physicists had been observing wave effects using light. And so as a result, people had drifted away from the particle view and said, no, it's really more of a kind of a amorphous effect that just spreads through space. It's not individual particles. Well, Einstein saw this prediction from Planck and said, you know, they are particles, let's call them photons. And so physicists came to call these photons. Now, Planck never bought into this. Planck got a Nobel Prize for explaining how thermal radiation worked, but he never really bought into this idea of photons, which was kind of the major discovery that he made. Anyway, let's take a look at what this would suggest. So let's say that we have photons of light, 450 nanometer in terms of their wavelength, the blue part of the spectrum. here's what the calculations look like. Now, going back to chapter 36, which we just went through, these are the formulas for energy. And if you remember, for photons, as best we can tell, photons have no mass. And so we're going to write that down. Mass is equal to 0 for photons. Well, our fundamental energy formulas from special relativity tell us that having no mass is no big deal. Special relativity is fine with that. You can still exist, even if you have no mass. It does tell us, though, that the energy of the photons is equivalent to its momentum times c, and that all the energy of photons is kinetic. There's no mc squared for photons, and so all the energy is kinetic, and that's not such a big deal. But it does tell us how much momentum, how the momentum and energy are related to each other. So let's say these are the two fundamental energy formulas from relativity. I want to add to those the two fundamental formulas from quantum physics. Now, I think we've mentioned these before, but now we're going to use these kind of through the rest of the semester. Certainly over the next 2 or 3 chapters, these are going to keep showing up. And that is that the energy of a particle tells us what its frequency will be. If I have a photon with a certain energy, I can determine what its frequency is. Now, if I know its energy, I can calculate its momentum. That's a simple relationship here. And if I know the momentum, I can calculate the wavelength. Now, what h is here is what's called Planck's constant. And we're going to see how Planck's constant was determined. But we experimentally can determine what that relationship is, and then we can carry out calculations. So Planck's constant in standard units turns out to be 6.63 10 to the minus 34 joules times seconds. So that's Planck's constant right there. This is a factor of c. And what I've done over here is this. I said, look, if the wavelength depends on momentum, I can take that momentum, at least for photons, and replace that with Pc. I can put a c on top. Turns out that I can calculate the wavelength using hc over the energy. So flipping that formula around, the energy of a photon I can convert back and forth between its energy and its wavelength. Now, up until now, we've probably been spending more time talking about wavelengths of light. And I'm guessing in all your science classes that's what happens. But now we want to introduce this idea of, wait a minute, let's flip this around. Maybe it's energy that's the most important property, more so than wavelength. If I know energy, I can calculate frequency. And if I know energy, I can calculate momentum. I can calculate wavelength. So I'm going to encourage you guys to start thinking in reverse and say, okay, what's the most fundamental property of a photon? It's energy. That's where everything starts from. Because when we start looking at other examples in this chapter, we'll see most things are based on energy conservation. So I want to start with energy of the photons. So anyway, if we have a photon with a wavelength of 450 nanometers, oh my gosh, what did I do? Okay, time to correct this. So this is 450, 10 to the minus 9 meters. Take the nano out. Ooh, I put the nano in and the 10 to the minus 9. I apologize. I need to get that corrected. The energy of this photon is 4.42 10 to the minus 19 joules. Now that's in joules. What we would like to do is convert that into EV. EV are going to be our go-to units when we're looking at energies. I hope you guys remember this from Physics 4B, right? That there are these units of EV that become very handy when we're looking at individual electrons and protons and atoms and molecules and such. So I took HC. See that factor of HC right there? Turns out that if I put that in standard units and then convert into EV and into nanometers, that combination HC is 1240 EV times nanometers. And that's accurate to 4 significant figures. This becomes really handy to use because we're going to use this equation or its reverse over and over and over and over again. This could become maybe the most frequently used equation for us in the course. And knowing that HC is 1240 EV nanometers allows us to do a quick conversion with that. Okay. Which I didn't include here. Oh no! Okay, that got dropped out too. We're going to see it show up though. All right. Oh, maybe it's this next example. Here we go. Photons from a light bulb. So they say we have a 100-watt light bulb, but only 3% of the energy is going into light. So we're going to say we have a 3-watt light bulb, not a 100-watt light bulb. So example 37.4, here is our 100-watt light bulb that turns into a 3-watt visible light bulb. And so they gave us this information in joules. What I'm going to do is I'm going to convert into EV units. So 3 watts is 1.88 10 to the 9th EV per second. Okay, so that's, and that can't be either, right? Okay, we're going to have to double check this one too. Let me move on to this and then see if this is going to be recoverable. Yes, I dropped a 1 there. Oh my gosh. So that should be 19, definitely. And this should be 19 here. So it's in my calculator. So looking at red light at 700 nanometers, those individual photons are 1.77 eV. And looking at blue light at 400 nanometers, those individual photons are 3.10. Now, they told us in the problem to pick something on average. They suggested using 2.5 EV to represent my average photon. So I took my 1.88 10 to the 19th EV per second and converted that into number of photons, and now I got the right answer. 7.5 10 to the 18th photons per second. So I got to make a note to get that corrected too. Not a good sign here with 2. Unfortunately, we're finishing up the lecture, so before we get to anything else. So that actually is probably a good place to stop for the day. Yeah, let me stop right there. Well, let me do this. Let me move to one additional slide. What we're going to be looking at next time, or we're going to start off with, is looking at that function. That is the Planck distribution. That's the formula, or the function that Planck discovered would accurately represent the distribution of light being produced in thermal radiation. Any questions? Stop by office hours, and we'll get those questions looked at.